Welcome to the second lecture of time independent perturbation theory. What happened in the last lecture was I have recorded the whole lecture, but later I found that the half lecture has been recorded, and the other half was not recorded due to some memory problem of the recording device that I am using. I have decided to record it again, and in this particular lecture, because it is just the hectic calculation, so I will show you this particular calculation on the paper, and it's just basic calculation. So let's start to calculate. So we were solving in the last lecture this particular equation to get the first order correction in wave function, the first order correction in energy, and the second order correction in energy. These are the three quantities that we are looking for, right? This is the first quantity that we will calculate, and this is the aim of this particular derivation. This is the second quantity that we are looking for, and this is the third quantity that we are looking for to calculate. So it is just simple. You just have to act these operators on these particular states. So it will be like H naught acting on psi n plus lambda common H naught acting on, so H naught acting on psi 1, it is phi n psi 1, and plus this W acting on phi n, and there will be lambda common plus lambda square, and it is H naught acting on this particular state. So H naught acting on psi, sorry, yes, psi 2, and this W is it has to be has to act on this particular state to get lambda square. So it is W acting on psi n 1, right? So you can calculate more terms, but we are interested in just the second order correction, up to second order correction. So we are just calculating the coefficient of lambda square. On the right hand side, so on the right hand side, these are, because these are just the scalars, so you have to multiply these scalars to these states. So it will be E naught into phi n plus lambda times E naught into psi n1 plus, and this particular quantity has to multiply it with this quantity to get lambda out there. So it will be en1 acting, oh sorry, multiplied with phi n, right? One more coefficient of lambda square. So it will be this term has to multiplied with this particular term, so it will be en naught multiplied with psi n2 plus this term has to multiply with this term, so it is en1 into psi n1, and this term has to be multiplied with this term, it is en2 multiplied with phi n, and so on. Now just equate these coefficients, right? Different coefficient of different power of lambda. So now equating coefficient of different power of lambda. So what we will get for zero order in lambda. So for zero order, because this term has no lambda, so it is lambda 0. Again, this term has no lambda, so it is just like lambda power 0. So if you equate the coefficient of lambda power 0, it will be H naught acting on phi will give you E naught into phi n. So this is one of the important equation for first order in lambda. First order in lambda. So for first order, you just have to equate the coefficient of lambda power 1. So this is the coefficient of lambda on left hand side, right? And on the right hand side, this is the coefficient. So it is E n naught into psi n1 plus E n1 into phi n. This is the second most important equation in this derivation. And third, for second order in lambda. So it is the second order. For second order, you just have to equate the coefficient of lambda power 2. So on the left hand side, it is h naught psi n2 w psi n1, and on the right hand side, this is the coefficient of lambda power 2. So just write it. E2 phi n, right? So this is the third most important equation, because these are the equation that we will use to calculate these quantities, right? So we are looking for this first order correction in wave function and this first order correction in energy eigenvalues, and this second order correction in energy eigenvalues. So these are the terms that we are looking for. Now before proceeding further, let me give you uh, one more information, is that here we are assuming that the new eigenstates of the state of the system after the disturbance are nearly same as they were before disturbance, right? So these are the states before disturbance. We have assumed it in the last lecture, and these are the new states after the disturbance. So because we have assumed that the disturbance is not that huge, so these two states are just nearly same, and also we are assuming that these states are normalized. So if they are normalized, we know that the uh, dot product of these two states has to be 1, right? So that is what the condition of uh, for the normalization or normalized states. So the uh, dot product of these two states has to be 1, right? Also, we have assumed that these new state can be expanded in terms of power series of lambda like this, and so on. So you just have to put this particular value of psi n in this particular equation. So you will get psi n, and just replace this particular psi n with this particular value. So it will be phi n plus lambda psi n1 plus lambda square psi n2 and so on is equal to 1, right, on the right hand side. Now just take the dot product of this particular bra vector with these ket vectors. So it will be phi n into phi n plus lambda is, because it is just the scalar quantity, so it will be out of the product. So it is just phi n into psi n1 plus lambda square phi n into psi n2 and so on is equal to 0. Also we know that we have assumed that these states are normalized states, and if they are normalized, then the dot product of that state with itself has to be 1. So it is the condition of normalization. So this particular quantity is 1, so it is 1, it is 1, so this will cancel to this and it will be 0. So it is lambda phi n psi n1 plus lambda square phi n psi n2 and so on is equal to 0. But this equation is polynomial in the lambda, and if this equation has to be true, then these coefficients separately has to be 0. It is just the mathematical consequence of this equation. So these coefficient separately has to be 0, right? So these separately has to be 0. So this is one more important equation, right? So these are the most important four equation, right? Equation A, equation B, equation C, and this equation D. You have to remember and you have to understand these four equations, because now we will use these four equations to calculate these three quantities, right? So now we are going to calculate these three quantities. Now for first order correction, right? So for first order corrections, and we are taking for first we are taking for energy. So in energy, now we have this particular equation B, and there it is, the energy. So what we will do, we will multiply this particular term with bra phi n, right? So we just have to multiply this particular term with bra phi n. So let me write this equation here. So it is h naught psi n1 plus w phi n is equal to E n naught phi n, sorry, psi n1 plus E n1 psi n1. So this was the equation number B, and what we have to do, we have to multiply this equation by bra phi n, right? So what will happen, it will be phi n into h naught into psi n1 plus phi n w acting on phi n. It will be phi n E n naught into phi psi n1. It will be phi n E n1 phi n, right? Now in this particular first term, if you act this Hamiltonian on this particular state in this way, so we know that we know the solution of this particular equation. If Hamiltonian act on these states, it will be E n naught, because we know the energy of this particular state already. If Hamiltonian act on this particular state, so it will be E naught, so E n naught, and the state itself, which will have this scalar product with this particular state. And because we don't know the W yet, it will be given in the problem, so we will not do anything with this term. So it is just as it is. In this case, this particular E n naught is the scalar quantity, so it will be just taken out of the product, and it is just the product between this phi n and psi n1. Again, in this case, the En1 is just the scalar quantity, so it will be taken out. It will be product between these two states. Now this particular value is 0, because I have shown you in equation number D. So this particular value is 0, we have proved. So this is just 0. So this term is 0. Again, this term is also 0 from the same equation number D. This is 1 because the phi n state are normalized state, and if they are normalized, then their dot product has to be 1, so it is just 1. So we have E n 1 on one side and equal to this particular term, which is pi n w phi n. So this we have calculated the correction, first order corrected energy, right? So it is the first order correction in the energy. It is the first order correction in the energy. So this was the first quantity that we are looking for, and we got this quantity by doing this very simple algebra.